So let's continue with, let's have a second look at the redox question again. And this time I'll be sure to go slow and make sure that I ask people questions or if they have any doubts or clarifications to make. And please stop me if I'm ever going too fast. That's something that I did not say last time and I totally regret it. And I should have stopped on my own even if no one reminded me, but that's on me. Okay. So he has Luca has n dials numbered 1 to n from left to right, and two sheets of paper for him to write on. So Luca's game starts with him setting the dials in some starting configuration, which then he writes in the first sheet. Luca does in the following m times. Choose 2 integers, write them down in the first sheet. Calculate the sum of the numbers on the dials between a and b inclusive, and write down the sum on the second sheet. And then the final thing you have to do is press the button once on all dials between a and b. And the dials go from 0 to 9. You increase, but when you're at 9, you loop back to 0. And so you're going through 10 states essentially. Okay, and given the contents of the first sheet, help them calculate the numbers on the second sheet. Okay, so we should get a larger sample. Okay, we'll do 7, 5. We'll do this sample input. And like this, I guess. Okay. Alright, so we need to figure out a way to approach the question nicely. So we're doing that sample test case out there. So we said we have n and m as our first two things. Then config. And then m, and then a query with a and b. So that's how the input's going to be. All right, so let's look at sample bit 3 because I feel like it's a good size. All right, so 7, 5. So we have 7 different telephones, or 7 dials, and then you're gonna have 5 queries, or 5 times where you select numbers A and B, and press the all in between. And then the initial configuration was 908. 1 3 3 7, and then the A and B, we had 1 3 3 7, 1 3 3 7, 1 3. What a boring sample input. But at least the number is large enough that I can explain the ideas on a tree. And it doesn't look too bad. Okay, so let's write out the numbers up top. 9081337. So the indices are 0, 1, 2, 3, 4, 5, 6. Okay, so when we first since it kind of hints that you're doing query from 2 points, and that you have 100,000 different queries and 250,000 size, you can see that an O of m log n solution will pass, and that's what we're going to go for, and that's why we will use a segment tree. But we have to use lazy prop, but to do that first we need to have our segment tree built, and then we'll talk about lazy prop. So the roots node, what will be the range, or what will the left and right values be for the node, the root node, the top of the tree? Let's start with Andy. Why don't you give an answer?
Wait, you asked for the top node?
Yeah, the left and right values at the top node.
Goes from 0 to 6.
Good. 0 to 6. And then that node, that gets broken up into two other nodes. Okay, and let's actually keep going down the list. Who's next? Arsalan. if I chop this range in half, what will the range of the left node be, and what will the range of the right node be?
Do you want both or just
Yes.
one?
Yes.
I gave you two options and you said yes.
Yes.
Okay. First one's 0 to 2.
Not sure about that. How'd you get 2? Remember, the way we determine the splitting point is by doing the left plus right over 2. And then like doing
sorry, it's 0 to 3.
Yeah, 0 to 3, and then the range for the right side?
3 to 6.
Okay.
4 to 6.
Yeah, 4 to 6, because you do not want to have two of the same stored values in different nodes. Like, you always want them to be in one unique location. Okay, so 0 to 3, 4 to 6. So that's just a simple split. Okay, Brianna, if we take this left node over here, that's not, okay. If we take this left node and we split it, what are my left and rights? Oh, do not. Okay, what are my left and right? Thanks for there.
0 to 1, and then 2 to 3.
Good. 0, 1, 2 to 3. Because 3 divided by 2, integer division, you get 1. That's a horrible 3. Alright, who's next? Eston. What would it be if we split 4 to 6 into 2 nodes?
That will be 4 and 5, and then 6 and 6.
6 and 6. And that is our first leaf node that we encountered. Okay. Who's next? Evan. If we split 0 to 1, 0, 1 into 2 nodes, what would the ranges be?
Girl?
Me or Evan?
Evan.
Yeah?
Yeah, you. Go ahead.
Okay. I just said it, but I think like Kevin.
Yeah, he went over you. I did not hear it.
0, 0, and 1, 1.
Good. Alright, and the rest becomes self-explanatory. You just keep splitting it up. 2, 2. And then I'll just draw this one a little bit further down. 3, 3. And then 4, 4, 5, 5. Okay. So that's how we build the ranges. Now the indexes in the tree, we said that for any parent that has an index v, the left child will have an index of 2v, and the right child will have an index of 2v plus 1. So, and we start off by saying that the root node is 1. So, this should be relatively simple. Gordon, what are the indexes in these two children over here?
2 and 3.
Yeah, 1 times 2 is 2, 1 times 2 plus 1 is 3. Okay, who's next? Ingrid, what are the indexes of the two children nodes here?
4 and 5.
Yep. Okay, 4 and 5. Who's next? Kevin, what are the two children nodes indices here?
6 and 7.
Good. Legolas, what are the indexes of the two children nodes here? If you're not sure, just say you're not sure, just to show that you're here.
I'm not sure.
Okay, the way we do it is if we have a index v for the parent, the left child going diagonally left will have index 2 times v, and the right child will have an index of 2 times v plus 1. So you have v equals 4. What's the left child going to be? Give it a shot.
8,
And the right child?
Yeah.
9.
Okay, good. Okay, and Lily, where are these two going to be?
10 and 11.
Okay, and Marco, what are these two going to be? Okay, he might be temporarily gone. We'll just move on. Matthew, what are the two indexes?
12 and 13.
Yeah, 12 and 13. And remember, you cannot split a leaf node because it's only covering one thing, which is the index 6. So you don't want to split it any further. So this is where we would stop with our tree. So let's put in our data. So we said that this was 9, 0, 8, 1, 3, 3, 7. That's from the data, the initial configuration, or you can see it here as well. Okay. So we have our initial configuration, and the thing is with the initial configuration is that the numbers that we see here, if we created a parent range, like if we took the parent of the two children and we just added up the two children values, you would get 9 and you would get 0. And technically, if you had to move everything in the range 0, 1, 1 to the right, or you press the dials on that one once, it wouldn't work because it wouldn't work properly to a point, because you would be adding 1 here, so you could just simply add 1. But here, you're going from 9 to 0. So the algorithm isn't necessarily just adding 1. So that's why in the original solution, we had a frequency array. Frequency array. And it would have data for indexes 0 to 9. Okay, so you would have data from 0 to 9, because if you had a parent, let's say if we had this 0, 1 over here, and we were putting the frequency array over here, we know that we have 1, 9, and we can just put that in over here. We have 1, 9, so the frequency represents the number, and then the value inside the index, or the value corresponding to the index, says how many do we have. So we have 1 of those, and then we had 1, 0, 1 of those. So we'd fill the rest with zeros because there were no 1, 2, 3, 4, 5, 6, 7, or 8s. Okay, and then from here, if we had to shift everything to the right, then it's just as simple as rotating things. So if we had to shift everything one to the right, then this 9 would come over here, and this 1 would move over, and then similarly everything moves over like that. So that's how it would work if you were in a if you were doing it as a frequency array, which works a lot better, because if you were trying to find the sum of all, because the main problem is but how do we find the sum of the numbers in any range? And so that can be tackled by the fact that like you have the number 0 and you have 1 zeros. Sorry about that. You have a 0, and then you say you have 1 0, and then looking at the 1s, you have no 1s. 2, you have no 2s. 3, you have no 3s. ... 9, you have 1 9. So to find the total sum in a range, you would just do a for loop from like I being 0 to 10. And I'm not doing this formally. And then you do I times frequency at I. You'd add that on to some sum value. Sum plus or equals sum the I, the index, times the frequency of I, which is how many of those do I have. So that's a simple way to counteract that. So using the frequency allows us to rotate everything one to the right or some amount to the right really easily. And then it also allows us to do sum really fast, because this is only looping through 10 things. So this is like 10 operations, you could say, but that's a constant, so it's just big O of 1. So that's still going to be relatively efficient. So we'd want to do it. We'd want to have a frequency array at every node. And so I pointed out that this was the frequency array for this node over here that covers the range from 0 to 1. So we'd have, this might not be the best drawing. We'd have, let's use green. We'd have 1, 0 initially. No, we'd have 1, 0, then no 1s, no 2s, no 3s, no 4s, no 5s, no 6s, no 7s, no 8s, and 1, 9. And remember, the index is the value, and then the number corresponding to the index is how many of those do I have. So then comes the sum query between two nodes. Like how we did it here was if we had like a frequency array for this node, which you should just have a frequency array for every node, even if it's a leaf. So this would look kind of not really necessary at first, but it allows for the code to be the same. So 0, 1, 2, 3, 4, 5, 6, 7, 8, and then you have 1, 9. And then similarly, you have 1 and then 9 zeros. Then you could determine the frequency array for a current node is just the sum of each of the sum of the two frequency arrays. And what I mean is you add up the frequency of the zeros and then you add the frequencies of 1s, add the frequency of 2s, and so on until you get to the frequency of 9s. Okay, so how about we do that part for now? Just do frequencies and adding them together. C++, let's just name it something random. I'll change it later. Okay. So we'd have our template code. That's not it. Include. Oh, my keyboard's in French. I don't know why I like having a lot of random keyboards layouts. I have Greek in there, just in case I need to do some math. Not like I know any of the letters. I just spam all of them until I find theta, usually. But it's just a hassle. Okay, so template code, and then we need a structure for the nodes. Struct node, not p, semicolon. Struct node, and we have data for the left and right range, and then the index is already stored, so that doesn't matter. And then we need a frequency array, so int freq, and it has a size of 10 because we're going from 0 to 9. So int freq at 10, and then after, for now, we're not going to introduce the lazy propagation. We're just going to go ahead with the code. But actually, what is the maximum value for n? The number of dials, 250,000. So just for a good style, we just have constant int max n equals 250,000. And then I like to add, like, let's say 5, just in case you're slightly overbound just because you handled something weirdly. Like, it gives you some headroom. And then we said that the segment tree array has a size of, who did I leave off at? I left off at Matthew. Rayton, what is the size of a segment tree array?
It will be four times the array size.
Yeah, 4 times max n. The array size is going to be max n. In this case, that's just a number of things. And by the way, if you've already solved redox and you've already know a good amount of lazy propagation, I give you permission to go do the problems I posted last week if you haven't gotten to all of them. I don't think anyone has finished all of them because that's kind of crazy. But yeah.
They're so hard.
I agree. They're very hard. So int array max. Actually, no, we don't need. Since it's 250,000 and they're all in one line, it's actually probably easier to store it as a string. So a string input, and then you don't need to declare the size of a string in C++, so that's good. And then we can go and actually get our input. So let's say int And then the order of input was actually over here, so I'm actually going to use that. So int n comma m. Take the
You're-
inputs.
Dying.
Oh shoot. Can anyone else attest the fact that I'm dying?
Yeah, you are a little bit.
Oh gosh. Okay, I'll try my best to go slow, and let me know if I'm dying for an extremely long period of time. Okay, so we're taking in our input, and then now after comes the string input. So it's literally just taking in cin input. So this is inputting the string, and then after you have all of your queries. So that's all of your queries. But before that, build the tree. So we just build our tree, and then we pass in the index, the left and right values at the current place. So assign left and right indices, or right bounds. So we just do seg v.l equals L and seg v.r equals R. And then after, we need to check if we're at a leaf, because we can't divide any further. So I'm typing this in, I'm just typing it in the chat so people can follow, just in case I can't, I'm cutting out a lot. So check if at leaf node, because you can't divide further. So if L equals R, and then here we need to assign our input to be like the index of the input. Assign index L, index of L in index. All right, no, assign the input at L as the only thing contributing to the frequency array. And so that just looks like, and so since it's a string, it would look something like, how do I write this? Segreed dot frequency at and then you take the character input at L, and then the way you the easiest way to do it is just -0, and then you add 1 to that frequency. The reason being is because it converts it to an ASCII value when you do subtraction of characters. So we know that 0 and 0 have the same ASCII value. 1 and 0, the ASCII value of 1 is just 1 greater than the ASCII value of 0. I'm talking about the characters. So that means that the doing input L -0 will give you actually the values 0 to 9 respectively. So we can actually do it like this, and then we just return, or actually just have an else statement over here, so you can divide further into 2 child nodes, and then we need to calculate our middle point. So we find that int mid equals, and then, so how's my audio now? Am I still cutting out a lot?
Not really.
Oh, okay.
No, but I hear a dog whistle in the background.
Oh my god. That is not a dog whistle. That is my mom cooking and it's very noisy. I close my room. I don't know how I can barricade that sound. Shoot. If I turn on noise suppression, then it's gonna be even worse.
Your voice is a lot louder. Don't worry.
Okay. All right. Let me know if I'm cutting out at any point.
That's fine. It's fine though.
All right. So we need to bisect, and our middle point is just left plus right over 2. Left plus right over 2. And then we split and build the 2 children nodes. And that is done by calling the build tree function to the 2 children. So build tree, and then the left child has an index of v times 2. The left is still going to be the L. Like if you split 0 to 6, the left value is going to be the same. And then the right value is the average or the middle point that we found. And then the right side, we see has an index of v times 2 plus 1. We went from 1 to 3 in that case. V times 2 plus 1. And then the node, the left is 1 greater than the middle point. So it'd be mid plus 1. And then the right side, the right end will stay the same. So 6 and 6, you saw that there. The left and right stay the same. And then here we talked about how we have to join the frequency arrays simply by just adding the frequency of zeros and the frequency of ones and then so on. And so for here we can just do a for loop for int I equals 0, I is less than 10, I plus plus. And then you do seg v dot frequency at I equals the sum of the 2 child's frequencies for each value. Seg of v times 2 dot frequency of I plus seg at v times 2 plus 1 dot frequency of I. Okay. Can you go? Sorry about that. So here we're just joining the 2 frequency arrays together into the parent node, and then that'll keep building upward and upward and upward, and then we're going to be able to eventually build our entire tree. So that is the first part of the question, building the tree and actually making it look like we can actually use a segment tree to do the problem. So we've completed the segment tree part of the problem, and now we have to work on our queries. Alright, so it says here that we have to choose 2 integers, a and b, write them down, calculate the sum of the dials numbered between a and b, and then press the button once on all dials numbered between a and b. Okay, so we need to talk about the complications with how problematic this can get. So let's say if I wanted to a query. Don't worry about that. That's just my sister's background. She's a big fan of K-pop. Some of you guys might be too. You might be able to relate to her in that aspect, but just trust the process. All right. So let's say you had 2 things in a row, 0 and 3, and 4 and 6. These were 2 a and b values that are right next to each other in the query, and then you had like 5 and 6, and then you had 4 and 5. Okay. So you would go hunting in your segment tree array by searching for the range, and then you'd see here that the left child will have all of our nodes, and then the right child isn't not going to be a valid path, because when you get here, we're working with the query 0, 3 for a and b. If we and then we see that the 4 and 6 does not include any of the numbers in the query range, so we just don't want to use those. So looking at the range 0 and 3, this has all the numbers that we need. So we can actually just answer our query Really simply, calculate the sum of the dials on numbers between A and B inclusive. And so before we do any changes, the frequency would look something like we have a 1, an 8, a 0, and a 9. So over here, the frequency would look like get a green color. A 1, 8, 0, 9. So you have 1, 1, no, 1, 0, 1, 1, no 2s, no 3s, no 4s, no 5s, no 6s, no 7s, 1, 8, and 1, 9. So as I said, you can do the query, the sum query, at a node by just doing for I between 0 and for I being 0 and then ending below 10. You just have a sum variable and you do I times the frequency of I. No problem. You just do 1 times 0, 1 times 1, 0 times 2, 0 times 3, 0 times 4, 0 times 5, 0 times 6, 0 times 7, 1 times 8, 1 times 9. Add those all together, you can get your sum.
Is it just me or did he?
That's a good question. Is it just me? Is it just Kevin?
I think you cut out for a little bit.
Okay.
I could hear him.
Okay, maybe both mine and Kevin's internets are bad. Okay. So we can answer a sum query really easily by doing I times frequency of I. And you add that on to some variable. But now comes the hard part. When you try to, now you have to press all the dials one to the right and move them all one to the right. So you're going to essentially shift everything to the right here, which isn't that bad at first glance, because if you look at it from the parent node, shifting it one to the right isn't that bad. And then this would cycle all the way to the beginning. But the problem is, the nodes below it are not updated. Like this node, the frequency array is not updated. So you would have to cycle those too. And the nodes below would also not be updated. Same for these nodes. All the nodes here are not updated. Like all the nodes that are in this range are here from 0 to 3. They have to be updated. Or eventually updated. And if you just go and bash them out and like say, okay, now until you reach the bottom for every single location, keep moving everything one to the right, one to the right, one to the right. Your worst case performance is if you were querying from the very top, and then now you have to cycle everything one to the right. And so your overall time complexity for one query would be O(n), which is not good at all. So the idea is for lazy propagation, if you notice what I did for the query over here was I did 0 and 3, but then after my next query is 4 and 6. So if I flipped everything on 0 and 3, and then I'd have to either do a bunch of changes here or do something to tell the computer that I need to do some changes. My next query happens to not, like, this next query in this example just happens to not touch it. So if I were to go and do the query for 4 to 6, when I went, if I'd go to my left and right, this time I would find that my left node is going to be useless because the range 0 and 3 is not included in the query range 4 and 6, whereas this node is necessary. And this is actually the node that this is fully inside of the query range. And so you'd have to do your changes over here. You'd have to flip all the nodes and then flip all the frequencies one to the right. And then my next query is 5, 6. Then I'd have to go down, once I would do something to tell the computer that I have to make changes and something happens, we have to figure out what that something is. Then I'd go down here, make the changes from 5 and 6, and that would involve going here, and then you see that this path works is something you need to change, and going like this, and updating 5, 5 and 6, 6 because they're not in the same range is what you need. And then 4, 5. Then you'd come down here and say, I need to update this one. But this 0, 3 was never touched at all. So if this was actually if we just did a regular cycle tree implementation and we actually bashed it out by going through all the children nodes or child nodes, we would actually waste a bunch of time because we never actually touched these. We never actually touched these for the rest of the program. So the idea is, the idea for how to counteract this is always do the work just before it's due. AKA, whenever you need to hand that work in to do something else, or whenever you need to finish the work in order to do something else that requires you to finish the work, do the work then. Don't do the work anytime before that. And that's the mind of a master programmer and a master procrastinator. Is to do the work just before it's necessary to be done. And don't take this advice in real life. Obviously, try to do your work as fast as you can. You'll benefit from it. But as far as from a procrastinator's perspective, you will always do the work just when you need it. So the thing that we're going to use is called lazy propagation. Actually, why am I typing there? Let's type here. Okay, let's make this a little bigger. Yeah, just cover it. Zoom in. What we're going to use is called lazy propagation. Let me just make sure I'm recording. Okay, I'm good. Lazy propagation. The idea is, just as I said before, be like a master procrastinator. Do work only when you absolutely need it. In this case, what we want to do is don't update a node's children until they are needed for a new query. And let's bring back our whiteboard just to show what I mean exactly. I'm saying I can update I can flip everything here because it's not that bad for one node. But what I'm saying is don't even bother updating anything below that node, like these two nodes down here. Don't bother updating those until you absolutely have to. Because then you're going to save time in case you don't actually need to update them ever. This will save a lot of time, and even in some cases make solutions go from O of mn to O of m log n. The reason why I say O of mn is there are m queries, and if I did all of them as 0, 6, and then I flipped them all, like if I was doing the naive approach I described earlier of updating every child, you'd have O of n things per, you have O of n updates per query, and then that translates to O of m times n as your total time complexity because you had m queries. But the lazy propagation only does it when you need it, and it makes it super fast to the point that its time complexity is reduced to a guaranteed O of m log n. And so that's the idea of lazy propagation, saving a lot of time and making solutions a guaranteed time complexity of O of m log n, because there's no edge case that can outsmart the procrastinator. You can't outsmart the procrastination or procrastinator. All right. So now the question becomes, how do I know when I have to update the children? And the way you do that is actually by just having the effective approach we will use is to have a lazy boolean, and like most programmers call it lazy just because we're working with lazy propagation, so it just makes sense to say, hey, make the boolean lazy. So we'll have a lazy boolean if it's true. For the cases is if lazy is true, we will need to update the children eventually, and then if lazy is false, we do not need to update the children. And in the sense of me saying we need to update children eventually is because this node was changed when doing the previous query. Okay. Any questions up until now on the idea of lazy propagation? Okay. So it's just as simple as adding some lazy thing to our struct. So bool lazy. And a cool thing about structs is you can do something. You can say equals false, and that means by default set the lazy variable equal to false. So everything you create, like everything that you create that has a type of node, like that's a node type, its lazy value will already be set to false. And this actually translates really nicely. Like if I know something about some node or something, like let's say I know int cost, and let's say if it was an initial cost of 5, in some case it's not going to be obviously we're not going to use the cost variable, but I'll just give an example. Then everything that you initialize that has the node type, its cost will initially be 5. So just a cool thing to keep on the side or to keep in the back of your mind. So boolean lazy equals false, and I say this is a lazy variable, and it's false because we do not need to update any children at the start as we build the tree. And what I mean is we never have to rotate until we get a query. Like the only time we start rotating is after our first query. We're going to rotate the nodes, then the next query, then we rotate those nodes, and so on and so forth. But at first we do not ever need to update or rotate any the frequency values. So every node's lazy value should be false. So when we set lazy to true in our program, then we will say, okay, we need to print out that this will be our effective no, what am I saying? When we set lazy to true after like we get our query range saying, okay, this is the node in which we can answer a query, but then since it says that we need to immediately update after, then we will update. We will say lazy is true, so that it makes sure it updates the children later, but it will also update the current node right now. Okay. So let's go ahead and actually see how this translates to our code. So we need to do our queries. So we need our A and B values to be inputted. And so we have M of those queries. So let's just have like for ints q equals 0, q is less than m, q plus plus, and then we take in our inputs A and B. Okay, and then we need to have some query function. But first, you should be cautious how A and B here are between 1 and n. So that means that it was actually 1 indexing. Last week I was talking about how I 0 indexed everything just so it'd be more clear. But I feel like that's actually unnecessary now that I think about it. Like, you can do it, but you could also like do that as this approach, subtracting 1 from the A and 1 from the B. And so this is converting from 1 indexing. It's better to say going from 1 indexing to 0 indexing, which means indexing from 1 to n to indexing from 0 to n minus 1. And now we need to have some query function. So that's where our query function comes in. And so this is the simple query here is just going to be adding I times frequency of I, since we have our frequency over here, and then we keep adding our frequencies. So we're ready to just use the frequencies for our sum query, which is relatively simple and relatively similar to all the other segment tree questions that we done before we touched the lazy propagation idea. So int query, and I say int because I know I'm gonna have to return some value. So the index in the tree, int, and then I'll say the query left and then the query right. Okay, and then first we're gonna need our left and right values from for the current node. Okay, let's get some more people involved in here. Yang, what's the first case that we should check with a query?
First case?
Yeah.
Not exactly sure.
Well, okay, let's say we were doing a query over here. Let's just make this full screen. If you're doing a query from if you're doing a query for 4,6 and you're currently visiting this node, would this be a valid thing to add to our query?
No.
Okay, so that means that so the idea for our first case is query range has to be check if query range is outside of node range. And so that means that if there are no nodes that like any of the indexes are not part of the query range, then we obviously don't want to have anything to do with it. So and this can be achieved by doing if the query right is less than the left, or the right is if the right is less than the query left. Because if you think about it in a tree, let's actually draw this. Let's say you had it on a number line. Let's say you had a QL and QR over here. If your left was over here, for like the query left and query right, if your node's left value was over here, and we obviously know that the node's right value is somewhere over here, these are completely non-intersecting ranges, so we know that they won't have anything to do with each other. We don't want to have this impact any of our queries. So this can be achieved by saying if query right is less than the left, and so that's what we have here. And then similarly, let's scratch that out. If we have a left and right, and then we had query left and query right, if this was the possible scenario, where, and this can be done by saying if right is less than the query left. So if either of those are ever true, you want to return some value that won't impact the sum. And what's the one number that when you add, that will never change a total sum? Yeah, English, just have you finish
3.
this off?
0.
The smallest or the biggest number?
No. Wait. I'm saying what number do you add on so that it doesn't impact any sum? Like, what number can you add to x such that its result is still x?
0.
Good. Return 0. And that is our first case. And, okay, and now our second case. Second case is... Alright, let's go back up to the top. Andy, what is the second case that we should check?
You should check if your query range is completely inside the node's range.
Good job. Query range is completely inside node range. It's kind of crazy how I just thought of drawing a diagram now. Diagrams really help in a lot of math and column side questions. So if we had a query range over here, QL and QR, and then our nodes range was L and R over here, we see that the query range completely covers the node range. And so we want to have everything in here be affecting our final answer. So this is less than or equal to QL is less than or equal to L, R is less than or equal to R, which is obviously always true because you're working with the left and right. The right is always going to be at least the same as the left. And then the right is less than or equal to the query right. And both have to be true. Both this condition and this condition have to be true. So you have to use and. That's a horrible and sign. I don't know what you call and signs actually. Okay. So if QL is less than or equal to L.
Ampersand.
Pardon?
I believe they're called ampersand.
Ampersand. Yes, that is. I think that is correct. I remember hearing that before. If the query left is less than or equal to the left, and the right is less than or equal to the query right, then we need to add on the sum of the I times frequency of I. The idea that we described that we want to check every number between 0 and 9 and multiply by how many zeros and how many ones and how many twos, and we want to add that on to a total sum.
Wait, Sat.
Yeah.
So it should be instead the node's range is completely inside the query's range?
Yeah, thank you. Node range is completely inside query range. Yeah. Okay, so we need to add on the sum of I times frequency of I. So let's actually do that right now. So that's actually I've actually described how we do it here. For I between 0 and then any at less than 10, let's have some sum variable and say sum plus or equals I times frequency of I. Okay, and then here it'd be some like for int I equals 0, I is less than 10, I plus plus. Actually, we should have some sum variable. Int sum equals 0. For int I equals 0, I is less than 10, I plus plus. We can say sum plus or equals I times the frequency, but that's inside the segment tree, the node's data, so seg v dot frequency of I. And then here you would return the sum. And I left a space here intentionally, and we're going to talk about a wacky thing that you can do later on with updating and all that stuff. And then third case, if the node range is not complete inside the query range, but if the node range wasn't complete outside the query range, what do we know about the relationship between the node and the query range? Who's next in line? Arsalan. Take a look at this diagram and tell me. If it's not completely inside...
You mean like if it's partially inside?
Partially. partially inside, partially intersecting. You got it. Partially intersecting. Now check, add on the queries for the two children.
Well,
So
there's two cases there, right?
Pardon?
It's either QL is less than L and QR and R is greater than QR.
Yeah. But we don't need to do that because we're already gonna return something if we're in the first case. We're already gonna return something in the second case. So if there's neither of those two cases, it's definitely gonna be the third case.
Oh, okay,
you don't necessarily need to put an if statement. But yeah, you got the idea right. But we don't need to actually put that. So if you could save some lines, why not? So return, and then we need to do the sum query for the two children. So the left child has an index of v times 2, and the query range will not change. It's still going to be QL and QR. If you change these, you're going to screw up. QL, QR, and then add the query for the right child. QL, QR. Why can I not type? Okay. So, we've done our query. And so down here we can literally just say query function, and the way just as a reminder, start the query from the root. So it has index 1. So you want to print out the query from 1, because that's the index of the current node that we're using in the segment tree array. And then it was between A and B, and I believe it was inclusive. Yeah, inclusive. 1, A, B, and then you print that out. Okay, so now we've done the query part of the question. Now we need to do the update part, which is where the lazy propagation comes in. And we could theoretically make our own function, and there's nothing wrong with that. But instead of creating a function and doing the 3 cases again, you know that in this problem specifically, keep in mind this is specifically to this problem, that the query range and the update range are the same for every time, because it says calculate the numbers on the sum between the values between A and B, so the query range from A and B, and then update all the nodes between A and B. So while we're doing the work of going down and checking every node, and then we hit the second case where we're completely inside the query range and we do the sum, we can actually put updates on current node over here, because the update and query ranges will be the same. Note that I did my sum query before I'm going to update the thing, so it will still have the same effectiveness, and then after I update, I'll return the old sum. So it's still going to print everything out. Okay. So to rotate a node, let's say you have 5, 6, 7, 8, 9 commas. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, let's put some numbers in here. 8, 9, 7, 0, 6, 1, 6, 5, 8, 3. And then we want to rotate it to the right by 2. So frequency array, original. And here we need to, let's say we had, let's just do rotate by 1. So, sorry about that. So we need to rotate everything to the right 1 to make it look like at the end, the 8 moves down, the 9 moves down, the 7 moves down, the 0 moves down, and so on, and the 3 comes back here. So it'd be 3, 8, 9, 7, 0. Oh wait, that looks. Let's put it up top, just so it looks similar. 3, 8, 9, 7, 0, 6, 1, 6, 5, 8, and then the 3 moved to the front. So new. You can code it by just saying. Alright, so you can swap. You can swap stuff, move things to the right, but your new frequency array and your old frequency array, you're just moving things to the right. But when you move things to the right, if you just say move everything to the right by 2, if I move 8 to the right and then replace it, I knock that out and I put an 8, then move this to the right. Alright, no, actually we're moving by 1. What am I saying? We move this 1 and we knock that, we put 8. This 9 is just deleted now. So we do not necessarily want that to be how we implement it. We don't because we don't want to knock out any values before we have to reassign those to a different location. So what we should do instead is have some temporary array, temp 1, 2, 3, 4, 5, 6, 7, 8, 9. Have some temporary array that's going to act as our method of storing our new, right? And then we assign the frequency new equal to temp. Okay, so first we should move 8 1 spot to the right. And so 8 goes there. 9 1 spot down. 1 spot to the right. Then move 7. Then move 0. Then move 6. Then move 1. Then move 6. Then move 5. Then move 8. And then move 3 over. So make the changes to a temp. Like put the new array in some temp array, and then say make the frequency of the node equal to temp, so we don't have any assigning problems. So we're gonna have to do some rotation like that. Okay, so over here, so int, and then let's have some int temp of 10. Okay, so what I'm doing is for every spot between 0 and 9. So I'm looping from 0 to 9, or from 0 going to 10, but not reaching 10, but not doing 10. So from 0 to 9, you should do temp at, and then something like you add on 1 to your current index, I plus 1 equals seg v dot frequency of I. The only issue with this is, what if you're at 9? What if you're at 9? Then you have to go all the way back. Like at index 9, you have to go all the way back to index 0. So 9 plus 1 is 10, but I need to be at 0. So the simple solution is make your I plus 1 mod 10. Instead of doing a case-by-case basis, I plus 1 mod 10 will work for all of them. And then after this, we do seg v dot frequency equals temp. Okay, so you can't necessarily assign an array to another one. So what we're effectively doing is seg v dot frequency equals temp, but instead we're just gonna loop through all indices and just say seg v dot frequency of I equals temp of I. assigning all values from temp to frequency array. And so this is effectively doing segv.frequency equals temp, but it's not going to break our program. You can just do list equals new list in Python, but not in C++. It has its wacky sides. So now that we've done that, we said that now that we've done that, we could just return our sum and done, and then we'd be updating our current node. But we need to use our lazy propagation somehow, because we'll need to update the children eventually, as this node was changed when doing the previous query. So here is going to be where we say segv.lazy equals true. So what I'm doing here is I'm letting like the next time this the program hits this range, I need it to 100% sure check that it's going to be shifting the children before assigning any values to them or assigning any values to the current node. And I'm going to do that by saying segv.lazy equals true. And so now we've completed all the parts to the query and the update, except the part that the procrastinators don't want to do until the last minute, which is updating the children. Update the children somehow. Okay. Segv.lazy. Okay. So we need to update the children. Whoops. So we have our void, and you can call it. You're essentially gonna update the children, which means you're gonna push your lazy down. So you're gonna move it down to your current children, and then they're gonna procrastinate as much as they can. So we can do void push down, or push lazy, or whatever. So push down, and then we're gonna put in the parameter is just the index in the segment tree array. And then so we need to update our current node in some way. So void push down int v. And let's take our left and right. So this is going to be the function where we update the children. So we first here, when we got here, we applied our changes to the current node. And then we just said, we applied our changes, we rotated the frequency, and then we did segv.lazy equals true. Now, there's actually a flaw to this, which is what we're going to see over here. When we do our push down, if we update the children, like the thing we have to do is ultimately make our current node's lazy value equal to 0, and that is done by updating your children, and that's if applicable. Like if you have children, you need to update them, but that involves updating the current node. Actually, no, this should work. There might be edge cases where it won't work, but we'll run across them if they happen. Okay, so our first case here is check if the node doesn't have children. If your node doesn't have any children, then there's no point in actually, like, you don't have any children to update or push down to. So we can just say if L equals R, and then there's no point in, actually, I didn't even assign. It's good to take the values of the left and right range of your current node. And if L equals R, or in other words, if you're at a leaf and you're not going to divide any further, then you don't have any lazy values to push down or anything you have to tell your children because you don't have any in the first place. So if L equals R, then we just make our lazy value 0, lazy value false, and because we know that's for sure not going to do anything. And then otherwise, we need to actually apply the laziness to our children. So that's done by seg of v times 2 dot lazy equals true. And then seg at v times 2 plus 1 dot lazy equals true. And then seg v dot lazy equals 0. Okay. So this is where we're going to see that we have some problems. Because what I've done essentially is I've pushed my lazy things to my children, and then I said seg v dot lazy equals 0. So there are a few problems with this. The first is two problems. All right, few problems. Problems with using Boolean lazy value. Multiple updates pending to children. If we have an issue where, like, the issue is, what if a node sends a lazy thing to its children twice? It's the seg v times 2 dot lazy was already equal to true, so there's no point. Like, if you say seg v dot lazy equals true, and then when you go down and push down to the children and you say seg v times 2 dot lazy equals true again, you didn't change anything. You're just telling it to update once, not update twice. So multiple updates pending to children will cause them to only think they have one update. And so our solution is, instead of using a Boolean for lazy, make the lazy value an integer. The integer represents the number of pending rotations or dial pressings. That's probably going to be a word, but I hope you get the idea. By using an integer for the number of times you need to press the dial, then you're going to say for sure, okay, I need to rotate twice, so I'm going to apply my rotations by that much. So let's actually go and change that right now. Boolean lazy, and instead of doing Boolean lazy, it would go to int lazy. And then initially there's 0 thing, you don't have to update anything, so it has 0 pending rotates, or it rotates to children. And so here it'd be seg v dot lazy equals 0. Seg v times 2 dot lazy. And then you say seg v times 2 dot. So the number of updates that the child node has depends on the number of updates. Well, it is adding on the number of updates that we just pushed down. So let me just write this and then I'll explain. Plus or equals seg v dot lazy. Plus or equals seg v dot lazy. Okay, let me explain. If your child already has 5 pending updates and then you pass them one more, you need to tell them that they have 5 plus 1, and then they'd have a total of 6 updates. And then, for example, if a child has 0 updates and then you gave them 1, 0 plus 1 equals 1 update. So that's the idea of why we need to update our children, and by adding on the lazy value from the parent to the children. These might be 0, and if the lazy values for the children were 0, then their values are only going to be what the parent values were. But if you have multiple updates pending for that one child, you want to add on the number of updates given to you by your parent. So that's why you have to do seg v times 2 dot lazy plus or equals seg v dot lazy. Similarly, seg v times 2 plus 1 dot lazy plus or equals seg v dot lazy. Okay. So that's the problem with using a Boolean as a lazy value. in most cases, you can have or actually in some cases, you can have a boolean as your lazy value. But this time, since you are changing it, and then you're going to add on and change, and it's going to keep cycling forth, per se. Like, you're going to add on changes, and they're going to influence each other. Then you need to take the total number of changes for your child's lazy values. And then the other problem here is, over here we've shown that we successfully changed the frequency, and we rotated by a certain amount. But what if we came across a child that had pending updates? Like, you came into your thing, you had pending updates. You can't use the sum query if applicable. Alright, problem. You came into the function, you as a node, came into the function with pending updates or rotations. And the reason why this is a problem is if you have pending updates and you take the sum, but you didn't apply the updates yet, then you're going to essentially have your old frequency values being multiplied together instead of the new ones, which is like the old ones shifted to the right sum. And the solution to this is call push down function inside of the query function. So if you have any problems, so by calling push down at the very beginning, I should specify inside of function at the very beginning. If we call it push down, we can call in our second line actually because we're just getting data that won't change. Push down at index v.
Doesn't it give me mod 10 the value?
This will cover it, but it's gonna have to change a slightly bit. Like, you know how we had I plus 1 mod 10? It's gonna be I plus something mod 10. I think you know what that something is, but I'll get into that. That is gonna be our part of a problem. So if we call our push down function here, then we're guaranteed to apply any updates to a node before we have to potentially do a sum query on it. So this is a point where the procrastinator has to do their homework. Otherwise, they mess up the program, and it's not good. So this is the location where you want to update it and like push down anything, because the procrastinator had to do the homework at this time or just before they're going to potentially impact the total sum. And we want to make sure that everything's all set in stone before we impact the total sum. Okay. And then, so let's say you come in here, and then you like you're a node, and then you are called, and then you walk in here and you say push down, and then I come up here and then I give my lazy value to my children, but I didn't apply this thing over here where I shifted myself. I never shifted myself. That was the problem. I never shifted myself, and that's going to impact the total sum. So there was no point in calling a push down function if you didn't shift yourself. So in reality, we don't actually put our updates here. This was a lie. We actually want to put our updates or reassigning values into our push down function. So it looked like that. Okay. Now the only problem is over here we're not necessarily shifting 1 to the right, because that depends on our lazy value. So Kevin, you were coming across this. What should we be shifting by? It's not necessarily going to be 1.
The value and the lazy value.
Yeah, the lazy value. We need to shift by the lazy value. And because we're doing a mod 10, we know that we're never going to actually run into problems. So temp at I plus segv.lazy, mod 10 equals segv.frequency of I. So we're shifting to the right, or shifting by a by segv.lazy to the right, or cycling by segv.lazy, or yeah, let's just say shifting. We shift everything to the right segv by adding on segv.lazy, and then we take it mod 10 just in case we exceeded our value of 10, or our maximum value of 9, and you were 10 or above. So temp at I plus segv.lazy mod 10 equals segv.frequency of I. And so what we found that our problem was child wasn't updating. Solution is don't listen to Sat, he was lying. Update the node in the apply changes to the node value in the push down function. Okay, that looks good. So we apply our changes, and then we say segv.lazy. Okay, and actually, to Kevin's point, segv.lazy can get really big if you keep applying updates and updates and updates. So it doesn't hurt to actually say segv.lazy mod equals 10. Because we know that moving everything to the right 10 was effectively the same as not moving anything at all. So by modding anything by 10, we're just making sure that segv.lazy doesn't go massive. I'm pretty sure it won't actually impact our final answer, but it can make things faster in the slightest amount. Okay, so over here, instead of saying segv.lazy equals true, we just add 1 to segv.lazy, telling the program that we need 1 more cycle shift to our children, to myself and my children eventually. So the next time, so if you're at a current node and it was impacting the sum, the next time that node is called, before it influences anything, it will make sure that it updates itself, and it tells its children that, hey, you're going to eventually need to update, take my lazy values, and then it will execute. Okay, and this should be good, because we're doing our updates in here, and then our push down function will be done in the query, so we don't actually have anything to call. Okay, let's run some sample data. Actually, before that, are there any questions or any doubts or clarifications that you want to make? Anyone wants to make? Okay, if not, let's actually test the sample data. Okay, so we have 75901337, and then our data here. Paste. Ooh. Okay, first of all, I made a mistake of not doing cn.sync with SDI0 and cn.tie 0. Second of all of my resulting values were 0. And I scan my program and try to see where I had where my mistake was. My pushdown looks good. My query looks good. Oh, my build tree. Let's just look at that. It looks fine. My struct was made correctly. But I just realized I never built my tree. Like, I never called the function to initially build the tree, and that is a very big mistake. If I didn't build my tree, then everything would just be set to zeros, because C++ default sets variables to 0. So void build tree, we need to call it from the root, and then the left and right indexes 0, 2, and -1.
LOL.
Yes. It's a very laughable mistake, but if this was happening on a contest, I probably wouldn't have panicked and took 5,000 times the time to find it out. Alright. 17, 22, 1, oh gosh, 127.5. Okay, so this is the part where I say, what did I do wrong? Okay, let's have a look. So I update my node. It doesn't hurt to call my pushdown function over here. Let's try that. It probably won't do anything, but nope, that does not seem like the right answer. Okay, let's keep searching. Sum plus or equals I times seg v dot frequency of I. Seg v dot lazy plus plus. Yeah, I should definitely be pushing down because I'm actually no, it doesn't matter. I don't think it matters actually. Okay. Temp at I plus seg v dot lazy mod 10 equals seg v dot frequency of right. Looks good, I think. Seg v frequency of input of L minus 0 plus plus. Yeah. Okay. Alright, does anyone have any questions? I will try to find the error and I'll let you guys know when I find it. But does anyone have any questions as to what I even did? Or anything about this? Because remember, it's okay to ask.
Sat, I have a question.
Yep.
Okay, so if you made like some update range function instead of putting it all inside query for some different function, some different question, I guess.
Sure.
So if your update range is completely outside the node range, you do nothing, right?
Yeah.
And if it's completely inside, you just set your lazy value and stop.
Yeah.
Right?
Yeah.
Then what happens when you have a partially intersecting range between your update range and your node range?
Let's actually okay, alright, so your update function is going to be a void function, correct? Because you're not actually returning anything.
Yeah.
So if you check your first two if statements and it doesn't satisfy either of those, just call the update function on the v times 2 and v times 2 plus 1 with the same update range, and then it should execute for what is going on. I have no idea. Okay, so I'll just ignore the replit. If you just call the function right after the two if statements, it will work. You just literally just do update at v times 2, update left, update right, and then next line, update v times 2 plus 1, update left, update right, and then that'll go to the children, because eventually you'll either be completely inside or completely outside. You'll never forever be completely intersecting. So you just call the function to the two children.
So after you recur for the two children, do you have to update the node you are currently at after?
Okay, actually, that might be my error. That's a good point. You know what? Let's make an update function, because I think you actually bring up a good point. I think that is actually my error. I tried being tactical and that just failed me. Okay, so void update. Int v, int, and then let's call it ul and int ur. Okay. Void update. And then, okay, so the first two lines here are going to stay the same. We want to update we want to push down anything if necessary. I don't need to comment that. Okay, so yeah, I actually think that you're actually correct on this one. Okay, so if ur is less than L or r is less than ul, it's the same idea as the qr is less than L or the r is less than ql, because you just, if the completely non-intersecting ranges, then you just break out of there, return. You could just do else if or else statements as well, but you just return, and then that case is automatically just out of the window. And then second case, if ul is less than or equal to L and ur is less than or equal to R, then we need to update or do something here with updates, and then your final case is calling the updates. The final case is calling the updates on the two children. Update v times 2 plus 1 ul comma ur, and then reset the parent values. What I mean is, up here in our build tree, you know how we did, like in general, we called the build tree to the two children, and then we use the data to recreate the parent data. You want to do that again. So it's most of the time going to be the exact same as everything under the build tree function for the two children. You want to use the child data to make the parent data. So, and this works because since you're going from the root to some parent to its child, which is also a parent, and you keep going down, 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 you're going to update some, eventually the thing above the thing that you update, this will get updated, and then its parent will get updated, and then its parent will get updated, and so on and so forth. Does that make sense?
Wait, Sat.
Yeah.
Could you repeat that part again, please?
The last part?
Yeah, just what you just said.
Okay, so when we call the update function on our two children, and then if something changes with them, with either of the children, it could be both. Actually, it will never be both, actually. If something happens with either of the two children, then your parent value has to be reassigned. Like your parent value has to be your parent value depends on something with the two children values. So in this case, our frequency of the parent value depended on the frequency of the two children values. That's why we use the segment tree in the first place. So what we do is reassign the all the things that are inside that are stored in the parent value. They're like not like the left and right range, because that won't never change. But things that will be influenced by the children nodes. So in this case, it was the frequency, and this works by putting it recursively down here, because let's say actually this would be better on a whiteboard. Let's say you had some tree. These are circles, not zeros. Okay, now let's say you had to update this node right here. Oh, it looks like Christmas colors. Okay, let's say you had to update this node right here. You did something with that node. Now you have to reassign this parent's node, this parent up here, this one, because it's one of the children changed, so its values are not going to be the same. So what we did was we reassigned the frequency. So when we reassigned the frequency, it would go up here. And because we're in the recursive function, and how it worked was it kept calling to below and below and below, and so on and so forth. If we update the parent and we put it at the end of the function, because it actually went through, like, you started off. Oh shoot! You started off from the root. You went to the to its left child. You went to its right child. That's the you went part is this update calling to its children. So after you call the updates, you can do anything you want, and you can put anything you want, and it'll impact all of its parents. Like, so if we say update frequency, or update freak for parent, it updates this parent, and then its parent will update, because it's in the same it's in that same recursive call, and then this parent will update, and so on and so forth. They'll keep going up and up and up. Does that make it more clear?
Yeah, that helps a lot. Thank you.
No worries. Okay, so we need to do something with our updates. Is actually taking these lines here. So I tried to be smart and doing the updates in the queries. I found out for myself they should never do that.
Wait, why wouldn't it work if you like put that for loop like after the recursion in the query?
Because the thing is, we're returning. Well, are you saying like we put the for loop inside here, like the updating the frequency of I for the over here?
For the third case, not for the second case, right?
You're right. You're right. That's actually okay. Yeah, I'm sounding like a complete idiot now. That's also valid. Putting the updates over here and making it all one function. That is also valid. So you would put segv.frequency of I equals the sum of those two here. You can put that over here. That would work too. But eventually that becomes confusing. And although that will work for this question, it was, as like from personal experience just now, it was difficult to like visualize, and I completely missed it. So after experience for myself today, I found out that just have your own separate update function. Even if the query ranges are the same, just have your own update function, and it will be better. Like it'll be easier to visualize. Okay, so let's actually fix this. So we increment the lazy, we push down to our children, and then we just break out of here. Okay. Now let's try our sample data. Okay, now we have another problem. Oh no.
Is this still on? Oh, it is.
It gave complete different values. Maybe, okay, let me actually see if it's correct, because sometimes Replit has strange behavior. Okay, let's not worry about that. Wait, I RT'd? And TOE'd.
Oof.
Okay, how about I do this? Let me check my old submission I actually AC'd on. And if that doesn't work, resubmit this. Great, that submission works, but not this one. But the code is slightly different, so. Oh, you know what, let me... Okay,